Welcome to this explainer. Today, we're pulling back the curtain on a hidden hero in your home's electrical system. It's a component whose entire job is to do absolutely nothing until the one moment it has to save your life.
So, let's start with a bit of a paradox, right? There is a critical component in your home's electrical setup whose entire job, day in and day out, is to do, well, nothing. It just sits there, completely silent, waiting for that one single moment when it's called upon to prevent a total disaster.
That component is the grounding system, or pambumian. What it is, really, is a special, super low resistance path for electricity to flow from your house's wiring straight into the earth. You can think of the earth as a giant sponge. It's just so massive that it can safely soak up any amount of stray electricity, keeping it from causing any harm.
Yeah, the best way to picture it isn't as an active wire, but more like the safety net for the high wire act that is your home's electrical system. Without a proper ground connection, the whole system becomes what engineers call floating. And trust me, that's not good. It means it's unstable, unpredictable, and frankly, really dangerous.
Okay, so this safety net, it's not just some passive feature. It has three very specific, life-saving missions that it's designed to accomplish.
First and foremost, human safety. It's there to protect you from a lethal electric shock. Second, system stability. It provides a stable voltage reference, kind of like an anchor in an electrical storm. And third, it protects your expensive appliances. It gives dangerous fault currents an easy escape route, which allows your circuit breakers to do their job and shut off the power instantly.
Now, not all safety nets are built the same way. Globally, engineers use three main strategies, or architectures, for electrical grounding in low-voltage systems.
These systems are known by simple two-letter codes, TN, TT, and IT. And you know, the main difference between them is actually pretty straightforward. It all boils down to how the ground connection at the power source, that big transformer down the street, is connected to the ground connection at your house.
So here's the crucial point for us. For residential customers here in Indonesia, the standard that's mandated by the state utility, PLN, is the TT system. That first T means PLN's transformer is grounded, and the second T means your house has its own separate connection to the ground.
And this wasn't some random choice. It's actually very strategic. For one, it creates a super clear line of responsibility between PLN and you, the homeowner. It also saves a ton on infrastructure costs because PLN doesn't have to run an extra protective ground wire to every single house. And importantly, it helps isolate your home from certain types of faults that might happen out on the wider grid.
But, and this is a big but, this independence comes with a critical catch. Your personal safety now relies entirely on two things working perfectly. First, the quality of your home's own physical connection to the earth, and second, a mandatory safety device. Here in Indonesia, it's often called a GPAS, but you might know it as an ELCB or an earth leakage circuit breaker.
So what specific dangers is this whole system designed to defeat? Well, the threats are very real, and they are completely invisible.
The first danger, and it's the most common one in a home, is something called touch voltage. Imagine your washing machine has an internal fault, and its metal casing becomes live with electricity. If you touch it while standing on the floor, electricity sees a path to the ground right through your body. A good grounding system provides a much easier path, diverting that current safely away from you.
The second one is called step voltage. This is more of an outdoor risk, say near a fallen power line. A huge amount of current flows into the earth, creating these dangerous voltage ripples across the ground itself. Just walking through that area can create a deadly potential difference between your 2 feet.
And this really illustrates the stakes. While both are dangerous, touch voltage is especially lethal. Why? Because the path the electricity creates, from your hand down to your feet, goes straight through your torso and can disrupt or even stop your heart in an instant. This is exactly what grounding is designed to prevent.
Okay, so how do we make sure our hidden hero is actually ready to do its life-saving job? Well, it all comes down to that physical connection with the planet itself. And the rules for that connection? They're basically written by geology. And this is where it gets really interesting. The effectiveness of your grounding system depends entirely on the type of soil around your house. Wet, clay soil, that's a great conductor. But dry, rocky ground, that's practically an electrical insulator. This means you can't just stick a metal rod in the ground and hope for the best. It's not that simple.
It's this extreme variability that means you can't just install a grounding system and assume it's safe. It has to be professionally measured with special equipment to verify that its connection to the earth is strong enough to do its job.
And that professional verification brings us to a magic number. According to Indonesia's General Electrical Installation Requirements, or PUIL, a residential grounding system must have a resistance value of less than 5 ohms. That number, that's the official benchmark for safety.
So why that specific number? Well, a low-resistance path is like a massive, wide-open highway for electricity. During a fault, this guarantees the surge of current is huge, so big that it's instantly detected by your miniature circuit breaker, the MCB, or that special G-Pass safety device. They then trip the power in a fraction of a second, long before it can do any harm.
So to bring it all together, the TT grounding architecture used in your home, combined with a working safety switch, or GPS, forms your personal, active safety net. They work as a team. The ground wire provides the path, and the switch detects the current flowing through it.
This silent guardian is on standby 24/7, waiting for a fault that might never happen. But if it does, its performance is literally a matter of life and death. So the final question is, have you ever had yours checked to make sure it's ready for action?